So, Xiaohui, maybe tell me first how you got into your field.
In astronomy? Well,
Yeah.
I grew up as an amateur astronomer in my hometown in Beijing, China,
Mm-hmm.
and then I went to college.
You can see stars in Beijing?
30 some years ago, yes.
Okay.
You could actually see 4 or 5 magnitude stars there. Now you can see 0 magnitude stars,
Right.
maybe. Yep. And then went to college, majored in astronomy, and came to the U.S. to Princeton for grad school.
Mm-hmm. And how did you get interested in quasars?
So when I was a student, when I was still in China, we started a small project using a modest-sized telescope, trying to do a survey using sort of many color filters to basically mapping sort of the spectral energy distribution of many objects over a large field. And part of that goal was to find quasars. So as my undergrad senior thesis, I started writing a code to try to figure out how to look for very high redshift, very distant quasars. And that, in the end, it turned out to become my thesis in Princeton later on.
Mm-hmm.
So that's how it got started.
So maybe we should back off and talk a little bit about the history, because quasars have been around 50 years or so, and it was a pretty big surprise and a shock when they were discovered.
Right.
So talk about how we even evolved any understanding of what they are.
So of course quasars was discovered almost exactly 50 years ago by Martin Schmidt. It came as when people look for objects that they could identify as radio sources, and then they look for images in optical wavelengths and find these small blue dots. And when they look at the spectra of these things, they couldn't figure out what's going on. There are these broad emission features that didn't correspond to any particular element that people knew before. So it was Martin Schmidt who first figured out that these were highly shifted hydrogen lines that coming from hot hydrogen gas, and the redshift of these lines indicate these things must be extraordinarily far, and combine that with these things actually are reasonably, bright by a sort of a actual galactic astronomy standard, imply that they have enormous amount of energy going into these things to power them. So it was a surprise, it was a mystery for a while, that how you can have these very luminous objects in distant universe. Of course, they're sort of the thing that kick-started the distant universe studies, because very soon after the first discovery of quasars, they can be pushed towards a few billion light years away, almost in the first few years.
And nice aside, I remember talking to Jesse Greenstein at Caltech, and he talked about having quasar spectra in his drawer and just thinking, what are these radio stars made of elements that I don't understand? And
right.
Basically, so Martin Schmidt had a nice little leap just to realize what was going on.
That's right. So, and then after a few years, I guess people realized maybe after 10 years or so, the only realistic way of producing that amount of energy is actually through a lot of matter falling into very, very massive black holes. We're talking about millions or sometimes billions solar mass black holes. And when the matter falls into them, sort of the friction that during this falling process of this highly high velocity gas is going to actually generate a huge amount of energy that order of magnitude more efficient than actually basically nuclear burning happening in the sun. But of course that particular theory took a couple of decades for people to actually accept.
And it's a useful aside on just how we use logic or how arguments to understand these situations. What is it that just tells you that it can't be a great pileup of stars in the center of a galaxy, since they have a lot of stars anyway? Because we're talking about a gravitational engine, something completely different.
Right. Well, so another interesting thing about the property of quasars is they are really, really compact. They're really small. The angular size is very small. Nobody in sort of modern, at least optical telescope or any telescope, can really resolve what is going on in the center. And the other clue that people had quite early on was these things turn to be varying in the sense their brightness is not a constant over time, and they can vary to the scale of years, months, days, or sometimes in certain wavelengths even hours. This variability actually gives you a constraint on how big the system is, because basically the speed of light is the fastest way you can communicate. Therefore, if the thing is actually varying at a scale of a few hours, this thing cannot be much bigger or cannot be bigger than a few light hours across. That's the assumption. If so, it's very hard to dump stars or any other energy to a few light hour across, which basically means you can't put in the kind of energy that more than 100 times the total energy is emitting from the Milky Way into the size of our solar system without the help of something as powerful as a supermassive black hole.
And it's to just a casual person wondering about this. It seems a little weird to have black holes, which are supposedly black, being these incredibly luminous objects that we can see all the way across the universe. How does that happen?
Indeed.
Why are they so bright?
Right. So it's not the black hole is emitting. It's actually the process of stuff that black hole is sucking into its horizon, and before it just disappeared from us, those sort of gas or maybe individual stars in the process of falling into black hole that is emitting this light. From a sort of physics energy perspective, what the balance is when you are falling into a very sort of a deep gravitational potential well, if you will, you are losing you're losing gravitational potential energy. In the same time, you're sort of getting this energy out to the infinity. And after the physical process of that happened, how that happened is actually still not quite completely clear, except we think that the gas falling, like spiraling in to the horizon of the black hole, very strongly high velocity and very, very high temperature, and actually some version of the sort of just the friction, just the rubbing the gas against each other during this process is actually going to heat the gas into high temperature and emitting a lot of light from it. But the truth be told is that the detailed process of this, especially when you get close enough to the black hole, how the energy get out is still quite a mystery.
And people, the theory, of course, the basis of the theory was very soon after the discovery. In mid-60s, people had the supermassive black hole idea. But I think the astrophysics to simulate, say, what's going on is extremely difficult.
It's still ongoing. So that's why for quite a long period of time, people were, not everybody, actually a good minority of astronomers have doubt on that. And I think in the 70s, there were a series of debates and controversies about what these things are. These things really that far away as indicated by their redshift, or they gain their sort of apparent receding velocity by some other means? So there were a series of debate, and there were interesting back and forth about some evidence for or against the sort of a cosmological nature of these quasars. I think over time, as people discovered sort of more of the astrophysical environment of these quasars, especially the fact how they live in very massive galaxies, and later on, when people begin to actually discover or show evidence of very massive black holes do live in galaxies, slowly, very few people, or probably these days almost no people, talk about, not exactly no, but very, very few people talk about the non-cosmological nature of quasars anymore. But it was a big debate in the 1970s.
And then probably an important debate, because the cosmological redshift is the foundation of cosmology. And if there are other mechanisms for redshift, then maybe we don't know other things as well.
Yeah, that's right. So, yeah, go ahead.
So, and maybe another little historical aside, that quasars are very extreme objects, but even back well before they were discovered, we had hints that strange things were going on in the center of galaxies, right?
Yes. So, I mean, quasars is just probably the most extreme and most powerful member of the population we generally call the active galaxies. And the beginning of study of active galaxies actually go all the way back to the era when Hubble was around. And so people already see some of sort of the poor cousins, if you will, of these quasars, which are many times less luminous, many times less active than the full-blown quasars we see today. But some version of it already, people know it from so-called Seyfert galaxies, and other kind of active galaxies have been known for a long time.
And radio astronomy, of course, found sources that were hard to understand in the 50s and so on.
Yes.
And in fact, that's an interesting aside too, because the first quasars also were radio sources, because that's how we figured out what they were. But it's turned out now we have a more balanced view of how the energy distribution of a quasar is. So, what is the typical energy output of a quasar across the electromagnetic spectrum?
So quasars actually were the starting point of what I guess people like to call sort of multi-wavelength astronomy, because quasar has energy emission all the way from the hardest, highest energy photons in gamma ray to very long wavelength radio. So it sort of have a very broad emission, which is reflection of the kind of physical processes in many scales, in many kind of physical processes going on around the black hole in the center of the galaxy. But the fact that most of the emission actually came sort of in the broad range of ultraviolet to optical to infrared, and that's where these sort of active accretion and the active emission from the hot gas actually show up. But there's good amount of emission in X-ray as well. It turns out actually the original discovery of quasars in radio wavelengths, of course, but only a relative minority, maybe 10-15% also quasars have very strong radio emission. They were called radio loud, which probably related to sort of a relativistic jet get injected from the central engine of the quasar. But the majority of 80-90% of quasars actually do not have very significant radio emission at all.
Mm-hmm. And now that we have the tools to look at quasars across the electromagnetic spectrum, since we're looking at this emission that comes from the vicinity of a black hole, which are the kinds of study that get us the closest to the beast, that tell us the most interesting things about the black hole and its immediate environment?
So essentially the radiation of higher energy, roughly speaking, come from the more inner part of this quasar black hole environment. So if you really want to study what is going on very close to black hole, many of them have to resort into study of X-ray, study of very high energy photons coming from these systems. And they are things that you can see sort of begin to show relativistic signatures that have something to do with black holes in X-ray wavelengths, for example.
Mm-hmm. And you mentioned millions and billions of solar masses. I mean, what's the biggest black hole? Also, just as a useful benchmark, how do we measure the mass? How do we even know what the mass of such an object is?
So there are a number of ways of estimating mass of black holes in the center of galaxies, but all of them are related to essentially looking at the motion of either stars or gas near the black hole. Basically, Newton, using your Kepler's law, to state that sort of the velocity and the radius is in combination of velocity and radius of these gases emitting will give you a mass.
So you're close, but not so close you have to use general relativity.
That's right. You're looking at things that you think that the gravitational force is dominated by the black hole already, but you're not quite there that the general relativity, in fact, is important yet. So one way to do that for more close-by galaxies is actually looking at to look at orbits of stars, or orbits of population of stars near the black hole. And of course, the best example is to look for individual star motions near the center of our own galaxy, which is actually the best determined black hole mass among galaxies. And then when you look a little bit further, at least in the nearby universe, you can use motion of stars near the black hole to measure their mass. When you look for quasars, these methods become very difficult because you don't have the kind of angular resolution to measure the radius, and people invent various kind of proxies of, say, using the motion of the gas combined with sort of some kind of estimate of the size of black holes by looking at how the light varies, as we mentioned before, to measure mass of black holes in quasars, and they sort of give you a consistent result. And I think it's one reassuring thing is the way that you measure the mass of black holes this way, and when you compare that to the theoretical predictions of what kind of energy this black hole by accreting gas can produce, these two numbers are sort of roughly consistent with each other. So that tells you sort of our physics is probably more or less right, although just detailed astrophysics of how radiation come out of the black hole and what is astrophysics environment around it is there's still a lot of uncertainties. But overall picture is probably okay.
And just as you've alluded to it, what is the efficiency with which energy is created in a black hole?
So one way to put it is, we all know sort of the E equal to mc squared. Basically, that's the kind of energy you can generate from the rest mass of a matter. And for black hole accretion, you usually can convert about 10% of the rest mass into radiation. In sort of by comparison, when you are in the center of the sun, the nuclear fusion that convert from protons from hydrogen to helium give you 0.7% of the rest energy. So that right there is a factor of 10 to 20 more efficient than even burning hydrogen in the sun.
Right. Yeah, that's pretty impressive. Now you've alluded to a big issue in this whole field, which is when people saw these extraordinary objects, you of course wonder, are they just extraordinary, galaxies where something peculiar has happened, or does something like this happen to all galaxies? So maybe talk about how we started to understand the role of black holes in general in galaxies.
Right. So for quite long period of time, I guess the study of black holes and quasars and active galaxies and the study of the evolution of normal galaxies are sort of were two fields that somewhat related but not really very closely related or coupled together.
I mean, that's an important cultural point because I grew up with this too. And when you have these different research communities with their own conferences, they don't actually talk to each other so much.
Certainly that's what the case until when I was a student in the 90s, or still sort of just black holes or quasars or just weird things going on in the center of the galaxy that may or may not have anything to do with the overall evolution of the galaxy because the area that sort of the environment that we're talking about that affecting quasars is probably rather small compared to the total volume of the galaxies overall. But then there was a very important discovery in, I guess, around year 2000 or so. In particular, using the Hubble Space Telescope, people were able to begin to measure the mass of these black holes and detect black holes, not necessarily all active, not necessarily all like quasars, but at least there is a very big gravitational pull in the center of galaxies. And the fact is that for almost all the big galaxies, at least they look at, they could always find a black hole in the middle. And more interestingly is that the mass of the black hole in these current days or mature galaxies is strongly correlated with the mass of the galaxy itself. So that tells you somehow the growth of the black hole and the growth of galaxy are sort of in lockstep. People begin to throw out the idea called co-evolution of galaxies and black holes, and at the same time, there are a number of sort of theoretical difficulties in understanding galaxy evolution that could be solved by assuming black holes during their accretion process played a role in how to shape the formation and evolution of galaxies. So people begin to really link the quasar and active galaxy research and normal galaxy evolution research together, and these days actually become a very big field of research is to understand what exactly is the quasar doing there, especially not only what exactly is the quasar doing to sort of the black hole itself, but what's the accretion process, what is the emission coming from the black hole, because it dumps a lot of energy in the environment. How can it shape the physical condition of galaxies overall, especially exactly because the amount of energy is emitting. Maybe it actually expel a lot of gas from the galaxy, and maybe it affects how the galaxy evolve, especially how the star formation process proceed in the galaxies.
So this is a really important shift, and without oversimplifying it, so now people realize that the quasars, are just the examples of those galaxies with big black holes where it's in an on state. And so what is it telling us about what is the phase of the quasar evolution, or what are quasars? Are they a tiny fraction of every massive galaxy's life, or are they special in any way?
Right. So one way you can look at this is, first of all, it seems like every galaxies we look at today, in the local universe, as I said, as far as they're reasonably massive, they always have a black hole in the middle. So the question is, how do you form them? How did the black hole get there? The best explanation of how these black hole get there is actually through this quasar phase. And there are actually statistical arguments to say that that may actually be what is happening. So this is sort of an indirect evidence to tell you that since there is a black hole in the middle of a galaxy, it has to be active at some point in their life. And you can estimate what is the fraction of this black hole have to be active, sort of a round number, maybe 1% or so, which means that people have been arguing whether it was 1% of the galaxy are on in the on phase, in the active phase all the time, or is each galaxy has 1% of its lifetime having an active quasar in the middle. And I think the consensus now is probably the latter one, which means every galaxy, every massive galaxy, at least through some period of their life, probably 5 to 10 billion years ago, would have gone through a short period of quasar phase. And that's how these black holes gain their mass, is through accreting in the quasar phase. And maybe that's also how the black hole evolution helped to shape the morphology and the history of the galaxy.
And alluding back to the fact that these fields were different, I mean, this is a very important paradigm shift in our whole subject, really.
Yes, indeed.
And so there's nothing special necessarily about quasar, but something people might wonder is, well, you've got this huge gravitational pit at the center of a galaxy. How can you starve it? How can you stop it from being a quasar? Why don't they shine more?
So that's, again, tied to this overall how quasars and galaxies are in their host galaxies, their evolution are affecting each other and how they co-evolve that picture. One idea is that maybe quasars, through the sort of process we commonly call feedback, one way to put it is, if your quasar is accreting a lot of gas, a lot of energy, a lot of material into it, is becoming very bright, and this energy coming out of the quasar is actually a lot, and that can expel the gas that the black hole is actually trying to accrete. And at some point, the quasar will be so bright that actually it's going to expel a lot of the gas. So basically, it's going to cut off its own food source. And through this kind of feedback process, how the accretion affects the subsequent evolution of the black hole is actually going to stop the black hole from growth. And the same energy that stops the black hole from growth maybe also stop the galaxy from growing much bigger than it is, because it's going to expel a lot of the gas or heat a lot of gas in the environment of the galaxy as well.
I mean, the thing you're talking about, it alludes to an interesting aspect of our subject that, again, to the outsider, it seems a little interesting that, we talk about these processes and evolution and things that play out over hundreds of millions or billions of years as if we could watch it happen, when in fact we have to sort of piece together story by snapshots. So, and does that, it's a reliable process, and we can learn about these cosmic timescale processes by just surveys and snapshots, the things that we can do with our telescopes in our lifetimes?
Well, unfortunately, that's the only thing we have, I guess. We're getting better at it by surveying. One key there is actually in this snapshot you try to find the same kind of objects over cosmic time. You try to trace things together. Although you cannot see a movie of it, you can sort of at least find the same kind of object at different cosmic epochs and see how they're related, how the properties, both sort of statistical properties and the astrophysical properties of individual objects evolve with time. For example, you can trace the mass of the galaxy of the similar mass and see how they evolve, or you can trace the sort of the same population of galaxies in terms of their numbers and see how things evolve over cosmic time as well. But of course, that drives you to where we started, which is to carry out surveys of quasars and to make. Because one difficulty is, of course, when you go to distant paths, when you go to high redshift, things can be very faint from our perspective. So you have to carry out very deep surveys at sort of cosmological distance, which was not possible until quite recently.
Right. So that's what I want to get to now, of course, your work and especially Sloan. Maybe just talk for worthwhile about the Sloan survey? Because it's a pretty extraordinary survey. People are amazed when they realize how modest the size of that telescope was, all the things that happened.
I think Sloan survey actually started probably with some discussion of a number of sort of pioneering astronomers in the, I guess, late 80s, actually. I believe it started somewhere in Tucson when a few of these people, Jim Gunn, Don York, Rich Cron, a few of the astronomers in Princeton and Chicago began to meet and talk about it. And that was also the time when CCD detectors actually became possible, and people began to make big CCD cameras and begin to make sort of a spectrograph that instead of can take light spectrum of one object, can take spectra of many objects at the same time. So they realized that it's a time to actually design a dedicated survey. With a telescope, the only thing it does is to take digital images of the sky and to take deep spectra of many objects in the sky. And it took them another 10 years, or it took a couple 100 people another 10 years to realize this project, which is a dedicated, very wide field telescope, a 2.5 meter telescope located at Apache Point Observatory, which is next to the Sunspot Solar Observatory in New Mexico. And the amazing thing at that time was the camera was so big, by modern standards maybe okay now, but it sort of has a field of view of 7 square degrees, so it can take very wide field images, and this wide field images and digital wide field images, and reasonably deep, with good sort of software effort to measure the flux of all these things, actually allow you to study property of galaxies, and in our case to actually efficiently select candidates of quasars based on the colors, because there are a lot of stars on the sky, a lot of sort of stellar looking objects in the sky. Most of them are just regular stars, but you want to study quasars, you have to find them. You cannot take spectra of every object, there's too many. So the sort of the thing that actually I was involved in starting as a graduate student was to figure out what is the clever algorithm you can use to use this color information to sort out which one is your regular star, which one have the high likelihood to be a quasar. And then you turn around this, and then you feed this information to your spectrograph, and to just take spectra of these objects. When the spectra come out, of course you can see, if you see very strong emission lines, these are the quasars.
And this is a very different, I mean, people are maybe familiar with the Sloan survey for all the galaxies, hundreds of thousands of galaxy redshifts, but this was going along in parallel, right? These projects were all merged.
Yeah, so quasars counts for about 1/6 or so of the total allocation of spectral fibers that Sloan has. We remember the days when sort of the number of groups, people working with different aspects of galaxy, working with different quasars, sort of have this joint session of trying to bargain of who get how many fibers that make sense. So in the end, we sort of decided on this distribution of the vast majority of them go to galaxies, sort of map out the three-dimensional structure of galaxies, and a reasonable number of fibers would go to study quasars.
And it, just to put a historical slant on it, I mean, it transformed the number of quasars. I mean, in catalogs prior to Sloan, there were, what, 10,000 or something?
Yeah, there were about 10,000 quasars before Sloan. Now we're talking about, well, we passed 100,000 a few years ago. Now we're marching towards 200. We're passing 200,000 quasars already. So we're talking about 10-fold, 20-fold increase of the number of quasars we know. And not only that, of course, it's also not only the number, but there are two other aspects that are important. One is these quasars are studied, surveyed, discovered in a very uniform way. So they allow you to ask the tough statistical questions without worrying about sort of whether your selection is good or not. The other is because Sloan images sort of are sensitive to redder wavelengths than people used to before, that allow you to actually push the boundary of the most distant quasars to significantly higher redshift than people had before. So before Sloan was the highest redshift was 4 point something, not quite 5. And the highest redshift quasars that Sloan discovered was 6.4 also. And of course now there are new surveys that utilize sort of a big infrared detector arrays that the highest redshift now is a little bit above 7 already, which correspond to sort of less than 1 billion years after the Big Bang.
So let's talk about that, because that's of course you're a big subject. Why is it important to push quasars back to these earlier times, and also why is it challenging to do? Why is it a hard project?
So of course you want to find out when the first quasars, therefore when sort of the first generation of supermassive black holes form in the universe. That's one big reason. You just want to see the evolution. You want to see when the first thing came about. And actually, the difficulty there, of course, is distant objects are faint, so that's one. And when you begin to look for things that getting close to the earliest generation, you know that sort of there's a build-up process. So these things, by definition, are rare. There are not many of them yet. I mean, the universe were not full of quasars in the beginning. The universe has a lot of quasars at redshift 2 or 3. We're talking about redshift 6 or 7 now. They're 30 to 100 times less quasars than before. So they're rare. So the second problem is, so they're faint, they're rare. That require you to have a survey that cover a lot of area because they're really rare, and also go to sort of sufficient depths. And that combination is difficult in SDSS. And also because of the high redshift, so basically light from the quasar is pushing towards redder and redder wavelengths, you need to have very red sensitive detection to find them. And that's also the thing that Sloan were able to do that couldn't do before. So all these three factors, the rare, they're being rare, they're being faint, and they're being red, combined to make them very hard to find before. And Sloan was really the first project that could find a lot of these very high redshift objects.
And now, of course, at this point where it's redshift 7 or higher, they're almost not visible objects at all, and infrared is a harder game than optical.
That's right.
So what are the prospects for, what is the limit of this work?
Well, so there is a technical limit, there's an astrophysical limit. The technical limit is basically how deep and how wide you can go with your infrared survey. And it took about 10 years for people to carry out sort of the first really deep wide field infrared survey to find its first redshift 7 quasars. There are a number of projects using, again, dedicated telescopes in the infrared to try to do this kind of thing. One particular one is a 4-meter telescope called VISTA in Chile that built by a consortium European observatories. And then the ultimate way actually to push this is actually to go to space, because infrared is really, really hard to do on the ground because of all the problem with the atmosphere, both transparency-wise and the sky is much brighter. But in space you don't have either of these issues. So there are plans, at least there is a plan approved by the European Space Agency to send a satellite, which most of the called Euclid, which most of the purpose is actually to do a dark energy related cosmology survey. But in the process of that survey, you have to take deep infrared imaging or a very large part of the sky. That will allow to find distant quasars. Maybe if NASA will ever put up something similar to the WFIRST project people have been talking about, that will go even deeper. So technically, there are things on the horizon.
And just as an aside on that, that's sort of how the field works now. I mean, both for Sloan, for Euclid, and for WFIRST, you have to merge your projects. When you're doing these huge surveys, you're usually serving multiple goals.
Exactly. So, but then another interesting question in this game is astrophysically what is going on. We're keeping on pushing towards higher and higher redshift, but it got to stop somewhere. Quasars have to form. I mean, quasars didn't exist at the beginning of the Big Bang. They have to actually take quite a while to form the kind of objects that we see. That's actually had been a major puzzle for this field overall, because we keep on finding quasars at higher and higher redshift. Although they get rarer, they don't look much different individually. And that was a puzzle.
And they have heavy elements in their spectral features, almost
so
with the same abundance, or can that be measured?
You can measure the chemical elements by looking at the spectra carefully. They sort of have the similar abundance, which actually is more than the abundance of the element in the sun. So there have a lot of things going on. And these quasars are powered by sort of black holes. We can estimate their mass of still 10 to the 9 solar mass, so billion solar mass black holes. It become very uncomfortable for a lot of theorists to figure out how to form them so efficiently. That's been sort of tied related to what we talk about. We really don't quite understand how quasars grow yet. We certainly don't quite understand how quasars or these black holes started. It's sort of the most standard theory of how black holes started and how fast they can grow. It's getting very difficult for you to use this theory to explain the existence of redshift 6 or now redshift 7 quasars. So there have been a lot of theoretical work to people trying to come up with scenarios that may be only relevant in the early universe that can form very massive black holes in a very short period of time. The problem is you can't grow black holes very fast. You can only grow it to you can double the mass of the black hole every 40 million years or so, and there are just not a lot of 40 million years left when you talk about redshift 7.
So this is a fascinating part of the field, that we have this exquisite information from redshift 1,000, 400,000 years after the Big Bang, and then we have this gap that we're trying to fill in the picture, and reionization. Maybe you could talk briefly about that too. So the quasars are this sort of critical piece of filling in that part of the story.
Exactly. So figuring out how the first generation black holes show up is extremely important to understand.
Could they have been without surrounding galaxies? I mean, did the black holes come first?
There are all kinds of theory going around. There could be collapse of many stars together. There was a paper yesterday talking about it. They could be something to do with the direct collapse of dark matter related materials. People write papers about so-called dark stars. I'm not an expert on it, but with fascinating physics. And the other thing you mentioned is reionization. So that's another thing that quasars were very useful for, is when you get a quasar, compared to a galaxy, what it does is give you a very bright light source. So in addition to look at quasars themselves to figure out what's going on about these quasars, you can also study what is lying between you and a quasar, especially the gas lying between you and the quasar. Sort of quasar like a beacon, like a flashlight that lighting up the kind of diffused gas between the observer and the quasar. And the farther you go with redshift, the further you can probe this kind of gas phase that you can otherwise you're just impossible to probe because they don't emit any light. So you're looking at what this gas is doing to the quasar, especially in terms of absorbing light, sort of the primordial hydrogen, cold hydrogen gas. And that's related to a process what people call reionization, which says that, of course, after the Big Bang, the universe become cold through a process we call recombination. Basically, the universe is full of cold atomic gas. But when through the quasar observation we see at low redshift, we actually can tell the gas in the so-called intergalactic medium between galaxies are fairly hot. And the reason they are hot, diffuse gas was because things like quasars or galaxies emit a lot of photons. These photons heat up the universe at some redshift. So this reheating process, which reionization just means the universe gets ionized again, which is really a heating process. The reheating process is a signature of the first generation of galaxies and quasars were emerging in the universe.
And an interesting other puzzle, because people had trouble in the local universe finding where all the baryons were.
Yeah.
And it's quite easy to hide them in this form.
That's right. So when that happened, what had been a long debate or mystery or long uncertainty, it could be, people further knew it could be redshift of 6 or it could be redshift of 30. So these quasars allow you actually to put interesting constraints. One of the interesting discovery that we had from the Sloan quasars was when we took very deep, high signal noise, very deep spectra of these quasars, we begin to see a very rapid increase in the cold gas when you go to higher redshift, which tells you you're probably zooming into that epoch when the universe was just transforming from this cold atomic phase to this hot ionized phase. And so that's through a process, it was actually a prediction that this thing had to happen at some point, was a prediction made in 1964 by Jim Gunn and Bruce Peterson. Jim Gunn, the same person who invented SDSS. And people have been looking for this kind of signature of absorption from the cold gas for almost 4 years until sort of the highest Sloan quasars were able to reveal it.
And this is also connected. People have probably heard, JWST is supposed to look for first light, and astronomers are looking for first light. So these are related episodes, right? The first wave of stars or black holes or whatever formed in the universe.
You can look at the light source from looking at galaxies. You can look at the black holes from looking at the first quasars, or you can look at what are these galaxies and black holes doing to the overall environment of the universe by looking at these sort of absorption coming from the cold gas. All these three pieces will fit together, hopefully, with JWST, with new discovery of even higher redshift quasars, and with other probes like looking at sort of there are radio ways of doing it by looking at cold gas emission itself. There are ways of looking at the impact of these objects on the cosmic microwave background. So there are sort of 4 or 5 different ways. Hopefully in the next 5 to 10 years we'll come together to sort of review this, what we like to think is the last frontier, the last unknown episode in the evolution of the universe.
Right. Well, thanks, Xiaohui. You've given us a great window onto an exciting field.